Bismillahirrahmanirrahim. Welcome students to the online lecture of digital logic design. In the today's lecture, we will be discussing the Boolean algebra. In the previous lecture, we discussed the binary logic, and in the current lecture, we will be discussing the Boolean algebra. This part also belongs to the course learning outcome 1. First, we will discuss why there is a need to discuss this topic in the digital design course. It is very important to have a basic understanding about how uh, Boolean algebra works or help us in simplifying the circuits. Because the aim of this chapter or this topic is to optimize a given circuit, and how we can optimize it in terms of hardware. Maybe you can say about area. We can optimize it in a way that is more related to some mathematical calculations which are described in the form of Boolean algebra. So that's why we first need to have a little bit understanding about what is the Boolean algebra and how it can lead to a simplification of a circuit. So in the first part, we will be just having look at the mathematical definition and the explanations about the Boolean algebra. The first thing that we will be discussing here is the a set. A set is defined as a collection of elements or objects which have a common property. Simply, if we say that a certain object belongs to a certain set, we write it as X belongs to S, and if it doesn't belongs to that, we will write it as uh, X doesn't belongs to S. A binary operator, we will define a binary operator on a set of S elements, is a rule that assigns to each pair of elements from S a unique element from S. First, what we need to define is that what is a binary operator. For the binary operator, we will be using this symbol. This symbol doesn't mean multiplication here. It's just representing a binary operator. It could be addition, subtraction, multiplication, or any other operation. So the static here is just representing the operator. This operator says that for if we want to call any operator a binary operator, then it must have to obey this rule. And this rule is that for any pair AB, the result is C. Then the A, B, and C all should belong to that set S. If that's true, then we will say that this is the binary operator for this set. Otherwise, say if A and B are the belongs to this set S, but its result C does not belongs to this set S, we will say that this is static is not the binary operator for this set. So we are just discussing the things in the general terms and form of a static now, and later on we will discuss what does this static means. Similarly, we will discuss an other important property of the basic set, which is known as the a closure property. A set S is closed with respect to a binary operator if for every pair of element S, the binary operator specifies a rule for obtaining a unique element of S. We will discuss this through an example of a natural number. Say we have a set of natural numbers here. It's from 1, 2, 3, 4 up till infinity. We will consider it closed with respect to a binary operator plus. This is the binary operator plus. By the rules of the basic arithmetic addition, that say if we choose any two numbers from a set of natural numbers, A and B belongs to any numbers from natural number, its result should always be also from the same set. Means the C should also be the same from the natural number set. If that is true, then we will say that this set is closed, the next set of natural number is closed with respect to binary operation plus. And you can always verify that if you choose any number here. Say you choose 2 and 3, its result would be 7, which also belongs to the set of natural numbers. So in this case, the set of natural number is considered closed with respect to the binary operator plus. And now we will see another example in which this is not true. Say, for example, for the same set, if we choose the binary operator subtraction, which is represented by minus, then we can say that we cannot say that the if we choose two different values from the set of natural numbers, and their result or their subtraction will always result in the natural numbers, because if you choose this 2 minus 3, you will get a result of -1. A -1 is not a part of natural number. So this set is considered not closed with the binary operator minus. So in this way we define the closure property. Now we will discuss some other basic laws which are related to this Boolean algebra. Suppose we have again this is the static operation. It is representing binary operation. We will have the associative law in such a way that, say, if x, y, z are the three elements of a set S, then they must satisfy this equation. That if you take the first operand, solve the first one, and then the result is solved with the other, it is equivalent to solving the last two and then solving the result with the first one. If this is true, then we say that it obeys the associative law. This binary operator obeys this associative law. Similarly, for the commutative law, if we have two operands like x and y, both are belonging to certain set S, then in this case, if we change the position, then it doesn't make any effect in the result. So if you perform either x binary operator y or y binary operator x, the both results should be the same. Next is the identity element. A set S is said to have an identity element with respect to a binary operator on S if there exists an element E that which belongs to the set S that has a property that is similar to this one. Say that there should be a identity element E that if we apply that identity element on any particular element of set S, like say x is an element object from the set S, and there is an identity element E that again result in that original element x, then we say that this is the identity element with respect to this set. So for example, let's say that the element 0 is is an identity element with respect to binary operator plus, because if you say that x, you take any number x which belongs to a set of integers, and then you add a 0 in it, or you perform this thing or a 0 and have an addition of this in x, it will always result in x. So because E here is equal to 0. So in this case, for a set of integers with the binary operator plus, the identity element we have is 0, and so the E is 0. So we have to make sure that if this equation is true, that this element will be called an identity element. Very much related to the identity element is another thing, the inverse. A set S having the identity element E with respect to binary operator is said to have an inverse which also belongs to the same set S. There exists an element Y belongs to X such that if you apply this operator, then that will result in the identity element. It means that inverse will be exist only if this equation is true. Means there is some kind of inverse of x should be represented in y, so that if you apply the operator, that will result in the identity element. Say for example, in a set of integers, with the operator is plus, and you know that for this case that E is equal to 0, or the identity element is 0. You know that there is always, for any value of this set of integers, there would be a negative equivalent of that will exist in their set. Say for 1 there will be -1, for 2 there will be -2. So it will always obey this thing, because this is the identity element, this is its inverse, and this is the original element. So for a set of integers with binary operator plus, you can always say that there will be an inverse exist. But say if you have to represent it in a form of, say, natural numbers with the operator this, then probably you cannot say that, because there are no -1, -2, or -3 minus terms in that set, so it will not result. Similarly, we have another law which is very common. It is known as the distributive law. Generally, it is between the two operators. We are defining the first operator here as steric and the second operator as dot. Please kindly don't confuse it with the AND operation or the multiply operation. It's just representing an operation, just like this steric one. So it could be between, in reality, it could be between addition and subtraction, or it could be between addition and multiplication. So it could have any value, this operator and this operator. So if both of the operators hold this, then we say that that distributive law is obeyed. Now we will discuss a little bit about the history of this Boolean algebra. Even in your book, you can see that it has just only summarized the basics or the necessary points for the Boolean algebra. We are not discussing this in much detail. We just want to use the two-value Boolean algebra, which is most related to our Boolean logic or the binary logic concepts. So we just need to discuss this thing. The all other points are very well written in the book. You can just read them for the reference. But we will now moving on to the next important thing. We will not be discussing these Huntington postulates and the switching algebra in detail. We will be moving towards the two-valued Boolean algebra, and we will be discussing the properties which we have just discussed in the last slide. Say for the two-value Boolean algebra, we have set B, which has two values. Either it could be 1, or either it could be 0. And the two operators that we are defining here is that this and this. And these operators, you can say, are defined from this one, and you can clearly understand that what does this plus means and what does this dot means here, because this is actually representing the OR operation, and this is representing the AND operation, and this is the NOT operation. So actually now in this case, the plus is representing the OR operation and dot is representing the AND operation. We have already discussed these tables. Using the postulates, we can define two different properties. First of all, the closure properties. Because for the closure one, if you remember that the result should also belong to the same set, and for this case, you know that for if you are performing the AND operation or the OR or the NOT, if you are performing any one of these operations, this its result will always be equal to either 1 or 0, which belongs to the original set B. So for each of these operations, the result will be either 1 or 0. So all these operators are closed with respect to this binary set of 0 to 1. The identity elements, you can easily identify the identity elements for the OR one using the, which is represented by a plus sign. The identity element is 0, and for the dot one, the identity element is 1. The commutative law is very much obvious from the ray, because if you change the position, then it doesn't make much effect on the result. The results remain the same. Next is the distributive law, that say this is the right hand side and this is the left hand side, basically we have to prove that both of the sides are equal. If you see even in the books, sometimes that x dot y is just represented as xy. So whenever this is represented as xy, it's understood that it is representing an AND operation. So to prove this thing, generally we use the truth table method to prove these things. There are some mathematical calculations also available which can be used to prove these kind of theorems. But we will be representing or proving this theorem with the help of a truth table. In the truth table, first we define the inputs, because you see here we have three inputs, x, y, and z. We will write all the combinations here, because there are three inputs, so we will have a total of 8 combination. This is a very easy way to write all these combinations. Say if you are have 3 bits, 1, 2, and 3. This is the last bit. You first write 0 and 1 interchangeable. The first position will be 0, then 1, then 0, then 1, then 0, then 1. Similarly, and for the next one, what we do, we have 2 zeros, then 2 ones, then 2 zeros, then 2 1. For the third one, you will have 4 zeros and 4 ones. If you have, say, fourth term, that would have 8 zeros and 8 1. So this is an easy way to write the truth table for a 2 input, 3 input, or 4 input system. That for the first column you interchange at every row. For the next one you change after every 2 row. For the third one you change after every 4th row. And for the fourth one you change after every 8th. So to prove this thing, what we need to do is that we have to calculate the right hand side and the left hand side. First we calculated this term y plus z. It is very obvious that you have to look only at these first two columns here and perform the OR operation in that. And we know for the OR operation, if one value is 1, then we will have result 1. So if you look at this x0, sorry, y, and this is result in 0. In this case we have 1 1 here, we have this value 1 here, we will get 1 here. In both of these our values are 1, we will get 1 here. Both of them are 0, so we will get a 0 here. 1 1 1. So in this way we will first take the value of y plus z, and then what we have to do is we have to AND this with the value of x. So we will AND this result with x. In the case of AND, you know, if both of the values are 1 only, then the answer will be 1. So for the first case, say we have a value of 0 here, x is also 0, so we will get result is equal to 0. Similarly, this is 0, so the result will be 0, this will be 0, the result will be 0, this will be 0, the result will be 0. For say up till now, the result will be 0. For this case, now we have to check that whether there is 1 or not. In this case, this is 1, but this value is 0, so result will again be 0. For this one, we have 1 here, and this one we also have 1 here. So both of them are 1, so which will result in 1. Similarly for the next two cases. So in this way we will calculate this column. Now we have calculated the one side, and now we would like to calculate the other one. The other one is that the first operation is x AND operation between the x and y term. We can see that we have x and y here. We will just simply perform the AND operation, means it will result only in 1 when both of them are 1, which are only for the last two columns. So we will get 1 here, and then x with z. In this case we will only get 2 ones here, and here. And now what we need to do is we need to OR both these results. So we OR both these results. So if anyone places 1, the result will be 1. So only the last three columns will have value of 1. And now we need to compare it with the other side. So this was the one side and this is the other side. If you check, both of their results are same. So it means that these operators obey the distributive law. For the complement one, you can see that this thing is equal to 1. You know that this is the representing the OR operation here, because if x plus x complement, any time one of the value, at least one of the value will be equal to 1, because if this is 1, this is 0, if this is 0, this is 1, so it will always result in 1. Since we can also say that, because if say it's 0 plus 0 complement, say if x has value of 0, then
its complement will have 1, so it will result 1. One, it has value of x is equal to 1, then its complement have value of 0, then again the result is equal to 1. So this equation will always hold true. And for the AND operation, that if we have a complement here, x dot x complement or x and x complement, it will always result in 0, because if x has any value of 1 or 0, its complement have the opposite value, and only the one is can be achieved if both of them can be 1. From this equation we can see that it is not possible that both of them could be 1, so its result will always be equal to 0. Similarly, there are some other points that uh, the two-valued Boolean algebra has two distinct element, and you know that there are two distinct value. One is 0 and the other one is 1, and both of them are not equal. As we have told before, that plus is representing the OR operation, dot is representing the AND operation, the complement is represented by the NOT operation, and we have seen that the binary logic is a two-valued Boolean algebra. The tables that we discussed here, all the properties we have solved here, are similar to the one which we discussed in the last lecture of the binary logic. And means the AND gate, the OR gate, and the NOT gate operation are similar to the one which we have discussed in the Boolean algebra with the properties of plus and dot operator. Now we will be just summarizing some of the basic result and laws that are related to the two-valued Boolean algebra. First, we will discuss a little bit about the duality principle. The duality principle say that for any equation that is valid, for any statement that is valid, if we interchange the OR operator with and all the AND operators with OR, and similarly if we also change all the zeros with 1 and 1 with zeros, then the resultant equation will also be valid. For example, say if we are just discussing this postulate 2a, we are saying this that x plus 0 is always equal to x, means that if you perform any result with this operation, plus operation, which is representing the OR operation here, it will always result that x, the input number will be again the result, because you know that if any value is value of x is 1, then definitely result will also be the 1. So in that case x will be equal to x, and if say x is equal to 0, then in that case the result will also be equal to 0. So this statement will hold. And similarly, if we want to know what its dual equivalent is, what we do is that we have x here. First we will do is we will write equation x plus 0 is equal to x. First we do is we need to change the operators. So we will have a dot here, which will be representing or changing this thing. Now we have this. We will have to change this 0 with 1. This should always this will result in x. So what we have done is we have changed this OR operation to and this 0 value to 1, and this equation also holds. So if you have any AND operation with 1, that will always result the same number x again, because if x is 1, then we will get a 1 in the output, which is equal to x. If x is 0, you will get a 0 in the output, which is also equal to x. So this is the duality principle, that if you change the interchange the AND operator with the OR operators and OR operators with the AND operators, and change any logic level 1 to 0 and change the 0 levels to 1, then the resultant equation will also remain valid. Now we will have summarized some basic postulates here. We will discuss their proofs in a mathematical form in the next few slides. We have just summarized them. You probably don't need to remember all of them, but this table is very important whenever you have a simplification problem, or you want to know what's the result of a certain operand. You can just look at this table and solve the resultant thing. So we will be just discussing these in more detail in the next few slides. Say for the theorem 1a, what does that theorem 1a says? It says that for if we have an operator or, then if you or two same numbers, say x or x, that result will always be the x. And it is very clear that if you don't go even in the proof, you can easily verify that this is true. How it is true? That you know that because if number has either value of 1 or 0, so if it has value of 1 here, then it will also have a value of 1 here, which will again result in the value of 1, so which is belongs to x. Similarly, if it has value of 0, it will also have a value of 0, the result will also be equal to 0. So this is a very basic thing, you can understand it from the equation. But for if mathematical proof, what we do is we try to prove these things through the different postulate which we discussed in the last slide. Say for this one, to prove this thing, what we do is we take the one side, and from that one side we try to explain this thing. So first we have this thing. What we do is that we know that we can put this AND with one operator with any number. If you remember the postulate, from the postulate 2b, we have from that we have written it that for any number this x plus x, we have an odd AND operator with 1 at it. So if you apply any number or AND it with the 1, it will result, its result will remain the same. So we will just have addition of this term here. And from the postulate 5a, you can see that 1 can also be represented in a form of this thing. 1 is also represented in a form of this x plus x complement, because this term will always result in x term here, 1 here. So x plus x complement is always equivalent to 1. And similarly, for the last one, we have to apply the distributive law, which is the 4b here. So for the from the distributive law, what we will get is that we will multiply this with this here and this with this. So we will get the result which is equal to x plus x into x complement. So by getting this result, what we do is now with that x into x complement is always equal to 0. This was discussed in the postulate 5b, and if you perform OR operation with the x, it will always result in x. So whenever you are trying to mathematically prove this thing, you need to remember, or you need to have with you the table which we discussed in the last slide, because all these postulates are written there. So I am just writing their numbers here, so just you can always refer them and calculate all these terms from there. So in this way we generally try to prove any basic theorem. The other way is that you can prove this from a truth table, which is very easy. But for the Boolean algebra case, what we do is we need to represent all these things in the form of different postulates, that what points we have used to prove these things. So you can easily go back to the last slide and check that how we have solved this thing. Similarly, for its other part, which is that if you perform AND operator with the same number x and x, it will always result in the same number. Again, you can prove this thing from the similar kind of the postulate what we have discussed in the last slide. These are just the basic mathematics. For example, the first one, this is, you can say, is from the 2a part. The second is from the 5b. You can always refer to the last table and then calculate these terms. This is 4a. This is from the 5b. B, and the last one is from the 2B. So you just need to represent these theorems. Generally, there is most of the time there is a not a unique way to write these things. You may follow different path and you can result in different these postulates, but the end result should always be the same. We need to prove this thing. So we started with this because we have first represented if we add this term, it will not make any difference to the term, so we will add there. And we know that 0 could also be represented in a form of x into x complement x and x complement, so which was represented here as this one. Then from the distributive law we can write it like this, and we know that for x into x or into x complement will always result equal to 1, so that's why we have written 1 here. And we also know that for any number x, if we AND it with 1, it will results will always be the same number. So in this way we also have proved this theorem. So you just what you need to do is you need to have a copy of the postulates which we summarized in the last slide, and just calculate these terms. You may end up with different steps, but your end result will always be the same. Similarly, there are other procedures or other theorems which you can also prove that. The theorem 2a could be proved in this way. It says that if you or any number with x, any binary number 0 or 1 with or with 1, it will always result in 1. And it is quite simple. That you know that this statement is true because you can check it with the truth table yourself. For the mathematical proof, you may follow these steps. These steps again are from the same table. And if you have to prove its other counterpart or the other part of the theorem 2b, which is that if you for any number x, if you perform the AND operation with the 0, the result will always be equal to the 0. You know that for OR operation, if one of the term is 0, the result is always 0. So it's quite obvious, but you can always follow the mathematical calculation like this to prove this thing. And the second thing, this is for example for this theorem, this is proved by the duality principle. And what the duality principle is, that we apply the duality principle on this term. Basically, we change this plus to the OR operator, this OR to the AND operator, which result x dot or x and 0, and change the one with 0. This one will be changed to 0, and this one will also be changed to 0. So if you apply the duality principle, you can also prove that. Then we have the complement thing that we have already defined, that if you twice take the complement of a number, it will always result the same number again. Then we can also prove the theorem 6a and 6b in the similar way. We can also represent them through you can say truth table form. Say we have to prove this statement, that for this what we do is that we first have the input x and y. We calculate the or AND term between x and y here, and then we OR this result with the x input. So we can, from this way, we can prove that how our result is achieved. For this 6b part, you can say that it's also can be proved from the duality principle. You need to just calculate these terms at least once by with you, so that you have a basic understanding. These are not much difficult steps, and you also don't need to remember them, that how you step solve, what was the postulate number that you use, what was the other postulate number that you use. You just need to know these steps. These are just the common understanding. You can easily prove that, but you should do it at least once with yourself, so that you can get a good understanding of this. Then is the De Morgan's law. We will also be discussing this in much more detail in the future lectures. This is a very important theorem, which is slightly different from the ones which we have discussed till now, because this theorem's actual proof is about, you can say, 2 to 3 pages. So we will be just in this course we will just be proving this thing with the help of the truth table. Say They say that if you take the complement of x or y term, that's equivalent to ending the x complement into y complement, and its other counterpart is that if you take the combined complement x y, that's equivalent to calculating the x complement or with the y complement. So what we have done is we have taken the two inputs x and y here. We have the four combinations here. Then we first calculated all the required terms here, and you can see that for the result, right hand side and the left hand side, both of them are equal. So in this way we have proved the De Morgan's law. Kindly do go through these pages for more understanding, because for the most of the Boolean algebra part we have just summarized the basic results. We have not gone into much detail about each and every theorem and the postulates regarding it. So kindly just do go through these pages to have a better understanding.